Okay. Now we are proud to present Sergey Kryzhevich from St. Petersburg State University, and he will talk about invariant measures for non-autonomous systems and ergodic inverse shadowing.
Muito obrigado. First of all, I thank all organizers to have a honor to make a talk in such a nice conference, in such a perfect place. So this is my joint work with Professor Sergey Perugin, who works at the same university in St. Petersburg. And we are studying the problem which is related to ergodic theory, to hyperbolic dynamics, and to shadowing theory. So in general, our main question is the following. If we have, can we use numerical methods to model invariant measures of a dynamical system? And another question is, if we have a numerical solution which has some small proportion of big errors, can we use it to model our dynamical system? So I start with some basic definition. So we work with C1 diffeomorphisms of compact smooth Riemannian manifolds. Like this, we introduce orbit of a point. And if we have a sequence of homeomorphisms that are C0 close to our diffeomorphism, then we call this sequence numerical method, and we introduce trajectory of the numerical method like this. So on every step, we apply iteration gk. So, and the main question of the shadowing theory is that are orbits of f and g close? So there are two definitions in this theory. So shadowing means that if we have an approximate trajectory, whether or not exists a true solution that is epsilon close to this this so-called pseudo trajectory y sub k. And the inverse question is the so-called inverse shadowing, that is, given a true solution, could we expect that there is an approximate solution that is close to this this true solution? So though these properties look quite similar, they in general they are not, because for this direct shadowing, it is the property of the whole dynamical system. You cannot say that there is shadowing for a given trajectory, while inverse shadowing is a kind of individual property that is that can be true or not for a given trajectory. So, okay. So this is some basic reference on shadowing, on inverse shadowing that is more interesting for me in this talk, and some metric analogs of shadowing. So also I recall some definitions from topological dynamics. So a point is called minimal if you take closure of its orbit, and if you take any point of this closure, then the closure of orbit of f coincides with the with one of for x, which means that this set does not contain any proper closed invariant subsets. So we call point recurrent or Poisson stable if it is alpha and omega limit for itself. And finally, we call a point non-wandering if for any neighborhood of x, there is a point which comes back to this neighborhood. So this is quite well-known inclusion that is true for any homeomorphism, actually. And so here is a definition of what is invariant measure. So given a map F, we consider the set of all invariant measures that is convex and compact in weak topology. So, and there is a very well-known statement that links ergodic theory and topological dynamics that for any invariant measure, all points of its support are recurrent. This is a simple corollary of the Poincaré recurrence theorem. So the weak topology has a disadvantage that it is not, the definition has a disadvantage that it is not related to a metric, but this metric can be still can be introduced, the so-called Kantorovich-Wasserstein distance. So if we have two probability measures on our manifold, we can define distance between them like this. So this leap one is the set of all Lipschitz of all functions phi from M to R that satisfy Lipschitz condition with a constant equal to 1. So, and this metric, it corresponds to weak convergence topology. So, what can we do? Given a map, we can take the set of all invariant measures that corresponds to this map. So we call it M of F. Well, I call hyperbolic what, for example, Stefano called uniformly hyperbolic. So that is, so we still have a decomposition, but here we don't have limit, we have uniform contraction and uniform expansion. One more definition from smooth dynamics. So we say that a diffeomorphism satisfies axiom A if periodic points are dense and in the set of non-wandering points, and this set is uniformly hyperbolic. And what Sylvain already told us in his lecture, there is a well-known Smell decomposition theorem that in this case, all the set of non-wandering points can be represented as a disjoint union of compact, invariant, and transitive sets. So, and the last classic part of my talk is the following. So we say that diffeomorphism is structurally stable if any small C1 small perturbation of this diffeomorphism is topologically equivalent to the diffeomorphism itself. And it is well known that structural stability is equivalent to axiom A plus the so-called strong transversality condition, which means that these intersections are all transverse. And omega stability, which means structural stability for restriction on the set of non-wandering points, implies a weaker condition, that is axiom A and so-called no-cycle condition. What does this mean, no-cycle condition? So we have basic sets, and we can, if stable manifold of one basic set intersects with another, we can draw arrow from one set to another one, and like this, we can make an oriented graph of this basic set, and if this oriented graph does not contain any cycles, then we say that there is no cycle condition that is weaker than structural stability, and together with axiom A, it implies omega stability. Okay, and now there is a result about inverse shadowing and inverse shadowing, quite recent one. It was proved. This is a corollary of 3 results by Sergey Yurich Pilugin, Kazuhiro Sakai, and Kyon He. So they have proved that the C1 interior of the set of all diffeomorphism, that is a satisfied shadowing property, is the same one as the set of diffeomorphisms that satisfy inverse shadowing property, and also this, it coincides with the structurally stable diffeomorphisms. So the main problem for me is that, okay, if we have the correspondence between maps and their invariant measures, so what are continuity points? So we have any system is mapped to the set of invariant measures. That is a compact set. So we can consider Hausdorff distance between these compact sets in Kantorovich-Wasserstein measure. So can we say that these maps are continuous or not, and what are continuity points? So, and moreover, I'll show you that we can do this also for numerical methods. So for instance, let us have a numerical method, and we can take iteration of this method, and using classical procedure of Birkhoff averages, we can define invariant measures like this. So first of all, we define a kind of ergodic invariant measures that are limit points of Birkhoff iterates. So we can take limit points of these and define the set M sub 0. So
what do you mean by method? You mean you fix a family of maps to K?
Yeah, I have a fixed family of maps. I call it method. And for this, I can define numerical, invariant measure, whatever it is.
Right, but this is a fixed family.
Fixed family. Yes.
Which main principle is just iterates of one given.
No. They are different. This is fixed sequence, but the maps are different.
I know, but in principle, it could be iterates of one given map.
Yes. Yeah, it could be, and they show, and they have proved that if this is what.
It could be the same map.
Yeah, it could be the same map.
Okay.
And if this is the same map, this is the classical invariant measure, what I'm going to show. Yeah, and then we take for all points of x, we take union over x in K, and then we obtain a set, and we take its convex hull and close it. And what we obtain in the end, we call the set of invariant measures for the numerical method G. So first of all, we introduce so-called ergodic measures as limit points of Birkhoff averages. Then we consider them for all points x, and then we take convex hull and closure.
They don't satisfy any other condition. This is just for definition.
Yeah, this is because I don't have other invariant conditions, you see, Stefano. So, and what is interesting that if this is just answer to a question. If the method is generated by a single map, then this is a set of invariant measures in its classical sense. So this is quite a technical result, but yeah, I'll give you. In the end, I show you the first page. We have this in archive. So and okay, and secondly. So why do I need to introduce these invariant measures for methods? So if we have a sequence of methods that converges to a map F, then we can say that invariant measures of these methods, the sets of invariant measures, they converge to a subset of invariant measures for F.
What does that mean? In M or in K?
Okay, let me. They converge in K. So M is index, M is index so we have G1, G0, G1, G2, Gm. Okay, this is the index that enumerates map in the method. And K is K parameterizes the methods themselves. So, let them uniformly converge to F. So we have better and better numerical methods. And then what we can say that in the end, if K is large, we get a subset of a neighborhood of invariant measure of F. So this is a kind of upper semicontinuity. And yeah, here we can use Takens-Storer and stability result and say that this continuity is, since we have upper semicontinuity, we can say that continuity is typical in CK topology. But still we don't have continuity, so we don't have lower semicontinuity, and that's why we need another statement. We call it ergodic invariant shadowing. So we say that a mapping satisfies ergodic inverse invariant shadowing if given a trajectory, given a trajectory, yeah, there exists except the trajectory of a given method, such that it is close for almost all values of K. So what can we have? We can have a construction fixed point and the map and an orbit which spans the greatest proportion of time in small neighborhood, but it can travel quite far. So, and what we have proved that if we have an ergodic inverse shadowing, then we have continuity of this set of invariant measures. Okay, well, we have introduced something, we have introduced something. How can we relate to what we already know? It's much easier to deal with this ergodic invariant shadowing, and what we do, we can prove that, we can prove that if the set of non-wandering point is uniformly hyperbolic, then this is quite easy. Then we can prove that we have ergodic invariant shadowing. That's how can we prove this? Because we know that a pseudo trajectory spends almost all its life in a neighborhood of non-wandering set. This is a well-known fact. And then we use hyperbolicity. So this result is not really challenging. But it gives quite unexpected corollaries that, for instance, we can say that the interior of the set with ergodic invariant shadowing contains the set of omega stable systems. Yeah, I'm finishing. Which means that, for instance, the just inverse shadowing is a proper subset of ergodic invariant shadowing. So there are some systems which have invariant shadowing, but have ergodic invariant shadowing. So we can use numerical methods with big errors, but they don't have classical invariant shadowing. That's it. Thank you very much.